This is Bob Capetta, and this lesson is on conditional probability. So our first question says, what is the probability that a card is a jack given that the card has a face? We focus on the given statement, given that the card has a face, and we have to construct a restricted sample that describes that given statement. So which cards have a face? How many cards do we have? What are they? Well, Jack of diamonds, Jack of hearts, Jack of clubs, Jack of spades, Queen of diamonds, Queen of hearts, Queen of clubs, Queen of spades, King of diamonds, King of hearts, King of clubs, King of spades. That is my restricted sample. That's what is generated after the given statement. So we have a total of 12 cards for us to focus on. Of those cards, how many are jacks? Well, the first four: Jack of diamonds, Jack of hearts, Jack of clubs, Jack of spades. So our notation is the probability it's a jack given that it's a face card. 4 winners out of a total possibility of 12 following our given statement. 4 out of 12, or 1 out of 3, 1/3. Not surprising, face cards are jacks, queens, and kings. 1 out of 3 works in that model. Next up, we're going to ask, what is the probability that a card has a face given that the card is a jack? Focus on the given statement, given that the card is a jack. How many jacks do we have? Jack of diamonds, Jack of hearts, Jack of clubs, Jack of spades. That's our restricted sample. So after the given state, we construct the restricted sample. There's 4 of them. That's what we focus on. Of those 4, how many of them have a face? Well, Jack of diamonds has a face, Jack of hearts has a face, Jack of clubs has a face, Jack of spades has a face. All 4 of them have faces, so it's 4 out of 4. Probability your face card, given that you're a jack, is 4 out of 4, 1 or 100%. Because the set of jacks is a subset, a subcollection of the face cards. All jacks have faces, 100% here. But again, our concept here with the conditional probability is to focus on the restricted sample, what happens after the given statement, and then determine how many winners you have from that group. So here's our next question. At a certain school, first-year students are strongly encouraged to study a world language. The following Venn diagram demonstrates the number of students studying Spanish and French. So 42 study Spanish only, 6 study both Spanish and French, 21 study French only, and 11 study neither. So how many students is that total? What's our entire sample? 42 plus 11 is 53, plus 6 is 59, plus 21 is 80. There's a total of 80 students. Now, how many of them study Spanish? 42 and 6, 48 study Spanish. So we could certainly come up with the probability of studying Spanish would be 48 out of 80. How many study French? Well, 21 only French, 6 both Spanish and French. So a total of 27 study French, and 6 study both. So we've got probability of Spanish is 48 out of 80. Probability of French is 27 out of 80. And the both, Spanish and French, is going to give us 6 out of 80. This lesson, though, is on conditional probability, so let's look at building those conditions. So here's the first question I'm going to ask in that regard. What is the probability that a student is studying French given that the student is studying Spanish? Focus on the given statement. Given Spanish, 42 plus 6, 48 are studying Spanish. That is my denominator. Of those 48, how many of them are studying French? Studying French given Spanish. Given 48, how many are studying French? 6 out of 48 is the probability of French given Spanish. Flipping this around, what is the probability a student is studying Spanish given that the student is studying French? So we focus on the fact that they're studying French. The 27 is our primary focus here. Of those 27, of our restricted sample, how many are studying Spanish? 6. So we get 6 out of 27. So what have we done? We've established some facts here. Probability of Spanish, probability of French, probability of Spanish and French. Probability of French given Spanish, probability of Spanish given French. I want to verify the AND rule. So the AND rule for dependent samples, probability of A and B, is the probability of A times the probability of B given A. But the fact of the matter is this is the generalized AND rule. This will work whether they're independent or dependent. It's just if A and B are independent, B given A is the same as B. So let's replace A and B with Spanish and French and see if these hold. So we're going to look to see if the probability of Spanish and French really is the probability of Spanish times the probability of French given Spanish. Well, what is the probability of Spanish? 48/80ths. What's French given Spanish? 6/48ths. You'll notice the 48ths divide out, and the result would be how much? 6/80ths. Is that what we wanted it to be? It sure is. We said up here from looking at the Venn diagram, probability of Spanish and French was 6 out of 80. Can we see that? How do we know that's the case? 6 out of 80. We had 80 students total. 6 of them were in the middle. Hence, 6 out of 80, right? 80 students total. 6 out of 80 would be in both Spanish and French. So that shows us then that our AND rule is indeed verified, that we get 6 out of 80 using this rule. Probability of Spanish and French is probability of Spanish times probability of French given Spanish. Our next example is going to look at grades and academic standing. So we have a general education lecture that will have freshmen, sophomores, juniors, and seniors. The following table describes the final grade in the course and the academic standing. We're going to try to answer some questions about that. First question I ask is, what is the probability that the student is a freshman given that the student earned an A? Our primary focus is to consider the restricted sample, given A. So all I want to see is the A column. Everything else can be ignored. Of the A column, there's a total of 55. 55 will be my denominator. Of the A's, we have 55. Of them, how many are freshmen? 12 out of those 55. So our probability someone is a freshman given A is going to be 12 out of 55. Again, restricting the sample space to given A, how many are freshmen? Next question I ask, what is the probability a student earned an A given that the student was a freshman? Given freshman, now I just look at freshmen. I just look at this first row and ignore everything else. Given freshmen, how many freshmen do we have? 57. Of them, how many earned an A? 12. So our probability you're going to earn an A given that you're a freshman is 12 out of 57. So let's do a couple other problems that are in that same vein. How about the probability someone is a junior given that they earned a B? So just focus on the B column. How many B's do we have? 46. Of them, how many are juniors? 12. So that'll be 12 out of 46. And we'll do one more like that. Probability someone gets a C given that they're a senior. So we're going to focus on the senior row. Focusing on the senior row. Not too many seniors in our class, but 11 of them are seniors. How many of them earned C's? 2. So 2 out of the 11 were seniors. Okay, let's again go back to what we had before, and let's think about our AND rule. So the probability of being a freshman and earning an A, can we verify our AND rule from looking at our conditional probability? Well, looking at the box, freshman and A, 12 people total out of 159. So if I randomly select a person from this class, what is the probability that person is both a freshman and earns an A? 12 of them, this cell, freshman and earn A, out of a total of 159. Now we're going to go ahead and test the AND rule. So what is the AND rule? Freshman and A would be probability of freshman times the probability of A given freshman. So what is our probability of being a freshman? How many freshmen do we have? Freshmen in this first row, 57. So if I'm just randomly selecting a person, probability a person is a freshman is 57 out of 159. Now we want the probability someone earns an A given that they're a freshman. Probability someone earns an A given that they're a freshman. Given that they're a freshman restricts our sample size to how many people? 57. So of those 57, how many earned A's? 12 out of those 57. So what's going to happen when we multiply these fractions together? The 57s are going to divide out and the result will be 12 out of 159. Is that what we said before? Freshman and A, this cell 12 out of 159. And indeed, looking at the AND rule, our result is 12 out of 159. So that makes us feel pretty good. the way we read the table agrees with the and rule. So let's remind ourselves of that and rule again in terms of A and B. Probability of A and B is probability of A times probability of B given A. So we can generate a rule for the probability of B given A, divide both sides by the probability of A to conclude probability of A and B divided by the probability of A equals the probability of B given A. But I want you to think about what this means, right? Restrict the sample size to A. How many of those have B being true? Now, what else can we say? Just sort of reversing the order. Probability of B and A is the probability of B times the probability of A given B. If that's the case, I can then solve for the probability of A given B by dividing probability of B from both sides. So we can say probability of B and A divided by probability of B equals probability of A given B. But the reality is probability of B and A is the same as the probability of A and B. So if I wanted, I could rewrite this with probability of A given B on the left, rewrite probability of B and A as the probability of A and B divided by the probability of B. So those are some rules that we can use if we want. The and rule is big, probability of A and B, probability of A times the probability of B given A. But what is also important is recognizing what this means. Identifying the meaning of the conditional probability is what this lesson was about. And that will conclude it.